DeepSeek's really doing some interesting stuff with the transformer architecture. They're like taking the good old transformer architecture that we know and love and changing it in multiple ways to make it actually efficient to utilize, unlike the current state of the art, which is basically full attention. But we use flash attention, which is still full attention. It's just faster because you have a kernel. So yeah, it's cool to see DeepSeek doing stuff like this. This is a paper that came out a couple of days ago, and they basically propose this method of a somewhat sparse attention representation, and they show it actually does better than normal attention. That's a little suspicious because you would think, oh, what is sparse attention? Like, sparse attention probably wouldn't do better than normal attention. But yeah, I mean, it does make sense that it could do better. But we'll see in the results that they actually do better with sparse attention over full attention. But not only that, it's actually faster because it's sparse. And since they do some clever tricks to make this work really well on a not a CUDA kernel, but a Triton kernel, and they do some cool tricks in here. So pretty interesting paper. Let's go into how they do this sparse attention. So the main idea is we have our attention mechanism here. We have our attention block. It's split up into our query key value, and we have our quadratic complexity attention matrix, where these are our queries, these are our keys, and yeah, you do full attention. And this is O of n squared, where n is sequence length. So attention, we all know, love, and somewhat hate. The idea is, since we already have to block this matrix in some way to get to make an efficient kernel, why don't we start by saying, all right, so we're going to formulate an algorithm that is blockwise so that when we actually have to implement this on a kernel, it will be efficient. So I don't know if they started with the idea of we have an idea for a kernel and we're going to find out like an algorithm that fits that kernel, or we're going to start with a blockwise algorithm and implement that on a kernel because blockwise algorithms are efficient on a kernel, rather than truly sparse attention, where truly sparse attention would be like, I'm going to select maybe this, and this to compute. That's inefficient to compute because this isn't contiguous in memory, and you would have to load each of these indices one by one, and it's just not efficient. However, if you instead said, I'm going to load, say, this block into memory, and I'm not going to load the rest of this is really fast to do on a kernel because this is contiguous in memory, really fast to load, really fast to do computations on. So it's like a somewhat sparse representation that they're looking for. They're looking for a blockwise sparse representation. The first idea is like we have these keys, and we have these where we have query keys and values, and our keys and values we can represent in a compressed state rather than the full state that it's in. So our queries are of shape n, our keys are of shape m, and our values are also going to be sorry, I should add the dimension, n by d, m by d, and v values are of shape m by d. This dimension can be different. But the idea is we can compress the keys and the values. You can't compress the queries. Like, you can compress the queries. It's just a pain to do that because the queries basically are your sequence length. Like, this is your output sequence length here. The keys and the values, you're doing an inner product, or you're doing an outer product on the dimension or an inner product on the sequence. So you can change the sequence length of the keys and the values, and it doesn't really, it's not a problem. So the idea is, well, what if instead of, so we're going to keep the queries the same, but what if we instead compress the keys? Say, what if we do a compression where we take the keys that are next to each other and just take the average of them? So then we would have something of shape m divided by 2 and d, and our matrix is much smaller. It would be half of what it was originally. So the idea is we want to compress the keys and the values, but in a blockwise manner so that we can compute this efficiently in a kernel. So there are 3 attention mechanisms here that they're going to use independently, kind of independently. The attention that is being computed, so the attention matrix itself, those are independent of each other. The computations themselves the first computation and the second computation. The first computation calculates some indices. The second computation is going to use those indices. Or rather, the first computation does merges. The second computation calculates indices on those merged, and then those merged keys and values. And the third part is going to be separate. So I'll show each part. It's not too complicated. So the first part is here is called token compression. So they basically want to do what I mentioned above, where you're compressing tokens of the keys and the values. And note that everything is going to be based off one row in the attention matrix. We'll look at the whole attention matrix in the end, but everything's kind of based off one row because what you do for one row, you can do for the rest of the rows. And one row represents one query. So that would be a query of shape 1 by D. And that represents one output of your attention mechanism. So what we have here is this thing. And what this thing is doing is it is basically doing a sort of convolution compression mechanism. So let me just show you in picture form rather than explaining what this does down here. So essentially what we have is we have our keys. So our keys here, which are going to be of shape n by d. I think I'll write it t by d. So let's say this is a causal mechanism. So this will be of shape t by d. So t is going to be the token so if we're looking at the output at time step t, this is going to be our keys up to time step t. And each key has some dimensionality to it. So this here is going to be our input. Let's say we have an input of size 9. And what we're going to do is we're going to define 2 things. We're going to define a window size. In the end, I think they use a window size of 16 and a stride. They use window size of 32 and they use a stride of 16 in the end. I'm going to use 3 and 2 as an example, but just know that they use a window size of 32 and a stride of 16 in the end. So what we have is we basically just do a convolutional type operation. So we're going to take each window size. So we're going to iterate over our sequence here. And we're going to iterate over it in a convolutional style. So we're going to iterate over this using a window size of 3. And we're going to iterate over by a stride of 2. So you can see here, I have these windows here. The first window is looking at tokens 1, 2, 3. The second one is looking at 3, 4, 5. The third one is looking at 5, 6, 7. And the last one's looking at 7, 8, and 9. So normal sliding window with a stride of 2 and a window size of 3. For each of these, what we're going to do is we're going to take these tokens, and since we have a set window size, we can basically stack these tokens and throw them through an MLP. So for this, my example here is taking tokens 5, 6, and 7, so window 3. You do this for every window. So for every single window, you take these tokens, you stack them together. So this is just stacking them together along the dimension, throwing it through an MLP, and compressing it. So yeah, that's basically the idea. You take your tokens, you have a window, you slide the window across the sequence, and you compress it using this MLP. This MLP is shared, it's a convolution, it's a window that is sliding across over your sequence, and it's just compressing them by stacking the tokens in the window together and getting some output token here, which represents basically this averaged representation of these tokens. And you have some overlap, just that you have some overlap within your token representations. So I have an example over here, which basically takes this part here and it does the merge, except it doesn't throw it through the MLP. But this here would basically represent tokens 1, 2, 3, 3, 4, 5, 5, 6, 7, and 7, 8, 9. So that's what you have over here. And that's just what this is saying over here. it's saying you have your MLP. It's going to look at these indices here. I'm guessing they stack it. I think they stack it together and just throw it through the MLP. I suppose you could also add everything in the window and also throw it through the MLP, but I'm guessing they stack it and throw it through an MLP. So that is this part. One thing to note is that this this index here, so it ends at this here, and if you calculate it, it is one less than you would expect. So if we have a sequence of size 9, it would output this here, and this would actually cut off at this. So it would actually output these 3 here. It wouldn't output this last part here. And that's because we want a causal representation. So this here allows you to have a causal representation by sliding the window across segments up until the last segment. So it doesn't include the last segment because that last segment, it wouldn't be causal. This last segment we're going to do attention with. And basically, it wouldn't be causal because we would have information of the future attending to this token. So say we were looking at output 7. So say we were looking at output 7, and we included this token here, which included output 7, 8, and 9. Then technically we have information from token 9 attending to this token. And since we have information from the future in our attention mechanism, it's a slight information leak, but it's an information leak nonetheless. So the last token is not included. But yeah, that's literally the idea for this part. It's just this sliding window to merge these tokens together, and we can see that up here. Up here. This is what the attention mechanism looks like. So this is 4 queries. This is a bunch of keys and values that are compressed. So maybe this is a window size 16, 16, 16, and 16, or maybe with like a stride of 16. And these are just 4 of the query outputs, and you can see that the attention mechanism looks like this. So this is just what a part of the attention matrix looks like, and notice here this causal part here. That's what I mentioned before, where you don't include the last token or you don't include the last merged part because it wouldn't be causal. Like if we had, say, a token here, if this part of the attention was included, it's technically looking into the future. So that's what we have here. So this greatly decreases the amount of memory you had to use. If we have, say, a convolution of size 16, then this would shrink the attention matrix by a factor of 16, which is massive. For something that is quadratic, that is a massive compression. However, this doesn't have fine-grained information. Like you're basically smoothing out your sequence. So every part is representing a patch of whatever that sequence length or whatever that window size is. What they also say is, there are some tokens that are actually like really important, and we want to attend to those individually. So what they're going to do is they're going to take this and they're going to utilize this compressed representation to select tokens that are important. So let's go down there, and that's what this part shows here. Basically, what we're going to do is we're going to utilize this compressed representation to select blocks of tokens that are important. And note that I mentioned we're selecting blocks. We're not selecting we're not selecting these sparsely distributed tokens that are important. We're not saying, I want this token, I want this token, I want this token. What we're saying is we're going to take these blocks. These blocks are representative of these token patches, these merged tokens in a window, and we're going to use those to select important tokens. So that would give you this block, say, it basically gives you this block-wise representation, or this block-wise strategy. So let me go down to that. So we have the compression, and what we're going to do is we're going to use the compressed tokens to do this token selection strategy. So we are only looking at one of the queries. This is one of the queries here, and we're going to multiply it by the compressed keys. So I'm defining M as this here. This here is essentially the number of windows we have, so the number of tokens in our output after we do the merging. That's what this is here. So that would mean that our K is going to be equal to, they transposed the keys for what I had M by D, but they have D by M. But that's because you transpose it whenever you do the attention itself. So what you have here is you have your D by M, which is your compressed representation of the keys, after you do the convolutional merging up here using the MLP. So D by K, or D by M, and you multiply that by the query in question. So whatever query you're looking at right now, that you multiply by that. And then you take the softmax of that. So what this represents is this will represent a score for every patch, for every block in your keys. And that's what this is here. And you essentially have this these scores that add up to 1 for every block. So here we would have a score for this block, and this block that add up to 1. And that is based off the query that you're looking at. So yeah, I mean, it's simple enough. I have a diagram down here to show that. So I increased the number of patches a little bit. That was just because they had a second thing that they were doing. But essentially you have these patches here, which represent these compressed representations of your keys. You're going to send this through you're going to multiply this by your one query. You're going to send it through a softmax, and you're going to get this output. I guess you can call it a distribution, but it's not really probabilities. So it's just scores. So you have these scores for every patch that you're looking at. So I'm just going to assume that the output number of patches that we want is equal to the input number of patches. However, if it's not, you have to do this annoying, weird balancing strategy, and this is, or not balancing strategy, but redistribution of scores. Yeah, I would just look at if you're coding this, just code up the formula. It's a pain to look at. I don't know any intuitive explanation for this part, but it's basically just summing probabilities if you have, say, a different window size for your output representation. For example, if I were to have, say, 6 patches here, so if L was equal to 4, D was equal to 2, so L is my window size, D is my stride size, I can have a differing output window size. The indice calculations become, or the scores have to be recalculated because of that. But yeah, that's just done using this formula here. Additionally, they're using group query attention. So for group query attention, you basically share keys and values for multiple heads of your query. And what you do is you say, well, I need to add up those scores. So for every group in your group query, in your group query attention, you're going to sum up the probabilities. But essentially all you're doing is you're taking the compressed representations that we had before, you're computing these scores here, and what we're going to do with these scores is we're going to say, all right, we're going to take the top n scores, and we're going to take those groups and do fine-grained attention on them. So we calculate the scores just by doing an inner product on the keys, on the compressed keys and the query that we're looking at. And once we have those scores, and we do a recomputation if we have weird window sizes, but once we have those scores, we're going to rank them, and we're going to take the top n scores. And then what we're going to do is we're just going to concatenate the original keys. So note, these are not the compressed keys, these are the original keys within each window, or within each of these top n windows. So I feel like that is best represented up here by going back to the diagram. So what we do is we initially calculate all of these, or we initially compress these tokens for each of these we compress our sequence to these compressed token representations. For each of these compressed token representations, we're going to calculate a score. So for example, in this first row here, maybe this will have a 0.2, this will be 0.3, and this will be, say, 0.5. Then what we're going to do is we're going to take the top n, so in this case, maybe n is just equal to 1, and we take this block here, and we're going to do fine grain attention on there. So we're not going to take this key right here. This is just one compressed key. We're going to take all of the original keys and do normal attention like that. But we're only going to do attention on these keys with these keys here. We're going to remove everything else. But note, it's using this block here. And that'll be important later for the algorithm that they use. The last thing they do is they do window attention. So that's just normal sliding window attention. Basically, it's looking at some number of tokens in the past and attending to that only. So basically a convolution over your sequence. So yeah, that's what they have here. Essentially, if you have your attention matrix, it's just this diagonal attention mask, and it's saying for every token, I'm going to look W tokens into the past. In this case, they use 512. So for every token, I'm going to look 512 tokens into the past, and I'm only going to attend to those. So we have these three attention these three different attentions here. One attention is a compressed representation, which is very efficient, but it's kind of this average. It doesn't have a ton of detail. It's just kind of a good idea of it's this compressed representation of your sequence. The second part here is saying, well, we may need some information. We may need some fine-grained information from our original sequence. So we're going to utilize these compressed representations. We're going to recalculate which blocks are important, and we're going to do full attention on the important blocks, on the top end important blocks that we computed here. So this gives you some fine-grained information. The last part is saying, all right, so we know that typically the most important information in a sequence is very local. So we're only going to take a local window. This part here has been done before. It's not really new. This first part here is the new part that they introduce. And each of these are going to be calculated individually. So we're going to calculate this compressed representation. We're going to get a set of keys here. Using this set of keys, we're going to do attention on here, and we're going to get some output attention. So let me go down to the formula down here. So what we're going to do is we're going to iterate over all three of these attention types, and we're not going to compute attention together with them. So we're not going to say, take the compressed representation, take the window representation, and take the fine-grained representation, and do attention on all of those in one attention matrix. What we're going to do is we're going to compute attention for them individually and then add them together. So there are three different attention things that we talked about. There is the compressed representation, the selective representation, and the window representation. And once you have all the indices for the compressed and selection attention, you can then compute attention in all three of these ways. So this is summing the attention outputs for, this is our output at time t. We have our query at time t, and we're looking at the keys and the values up to time t. So this is going to do attention using the compressed representation. So this is just going to be the normal compressed representation that was initially talked about. And then we're going to add to that the attention for the fine-grained selected blocks. We're going to add the output of that attention, and then we're going to add the output of the window attention. So essentially what you're doing is you're performing three different attention computations, and then you're adding the outputs together, and you have this gate here, which is just an MLP using your input. And one more time, we're going back to the diagram. Sorry, I keep on moving around a lot, but that's because the diagram's all the way up here. One more time just to show this is we're taking our original sequence, we're compressing it, we're doing these three different attention computations individually, separately. We're adding the outputs together. We're multiplying them by a gate to get our final output. I just want to note this is three individual different computations. So let's talk about the complexity. So the complexity for normal attention would be O of n squared, where n is the sequence length. So the new complexity is going to be this here, if I did everything correctly, where n is the original sequence length, m is going to be our compressed sequence length, so whatever this is here. So if n is, say, if m was 16, or if L is 16, then it would be n divided by 16. L is going to be the window size. I guess this would actually be L prime. L prime is going to be our output window size. We'll just assume these are the same. So this is going to be our convolutional window size. N is going to be equal to the number of windows that we have. So this is going to be equal to the number of selected blocks that we choose. And yeah, that's what we have here. Actually, that would be a W times W. So our first compressed representation would have a complexity of O of n by m. So it's n by m because we have n queries. So we're computing an output for every query because we're not compressing our output. But we are compressing the keys, so that gives us a complexity of n by m, where m is the compressed representation of our keys. The selected attention is n because we have to iterate over all, again, we have an output for every query, but this is the compressed representation where this is just the number of blocks by the block size. So n is the number of blocks, L prime is the block size. So in this case, it would be 2 by, I think that's 8, so 2 by 8. And then this part here is just normal sliding window attention, where n is, again, is our entire sequence length because we need to compute an output for every query, and W is the window size, so in this case it would be 6, assuming you have an efficient implementation for all of these. This is easy to have an efficient implementation. This can just use normal, I think this part can use flash attention, assuming you can get the mask correct. The second part here, I will show in a second the kernel that they make for an efficient implementation of this. And this part here, I think there exist efficient implementations of sliding window attention because sliding window attention has been around for a while. But in the end, this the upper bound complexity would be n by m, because these are smaller in complexity. So yeah, you can see that this complexity can be a lot less than the full quadratic complexity. And that's probably why they get such good results. So let's go to the kernel that they make before I go to the results. Yeah, this is just mentioning the sliding window. This is mentioning, we have all these representations and then we can finally use them. And this here is the kernel design. So what they do is they have this Triton kernel that they make. This Triton kernel is composed of what you would normally see in a kernel. So you have a grid and you have a grid of these or you have a grid and you have a grid of these thread blocks that you're doing computations over. So the grid loop is going to iterate over the queries, essentially. So basically, you can see in the background here this attention matrix, and this is going to be, I think, this is specifically for the second part. So the blocked, fine-grained selected version of the attention mechanism. I'll talk about that in a second after I talk about the kernel, but just think of this in terms of the second attention mechanism, the selective attention mechanism. So what we're going to do is we're going to iterate over our queries, and every iteration, we're loading in a new query, and for each of these, we're going to iterate over the keys and the values blockwise. So this is important because iterating blockwise is very, very, very efficient. You can do computations really, really fast if you iterate blockwise. However, in a normal sparse representation, you couldn't do this because it isn't blockwise. But since it is blockwise, and we know what blocks we're loading in because we have the index set that we calculated, we're going to iterate blockwise over the blocks we know we need to load in. So we know what key and value blocks we need to load in. So for every query, we're going to iterate over the keys and the values blockwise. You can see here, say this one here. We can iterate over this blockwise by loading in this block, not loading in this block, loading in this block, and not loading in this block. And for each of these blocks, we're going to do the computation for attention. So that's just the inner product. Or rather, the inner product of this query here with this block of keys. And then we're going to, then you do softmax, and I think what they do is they do what flash attention does, where they store basically the denominator and calculate as they're going through the row, but they don't mention explicitly. They mention that basically they iterate through the query, the grid is iterating through the queries, and for each query you can iterate over this row blockwise, and for each of these blocks you basically load in the keys, you load in the values, and you do the computation, and you write that to HBM. So do this in fast SRAM and offload it to HBM. They note that since they do this using group query attention, GQA, they don't just load in one query, they load in the group of queries for one head. So they actually load in each query headwise or groupwise, where they load in all the heads for one of the groups, because all of those heads are using the exact same keys and values, and then they do the computations rowwise here. And then they iterate over the rows, updating the outputs for that group specifically. So I hope that makes sense. It's pretty intuitive. Coding the kernel, that's probably a lot harder, but the intuition they give here is pretty straightforward. Iterate over the queries using the grid, and in each query you iterate over the row using the indices for the blocks that you computed, or using the indices for the blocks that you want to load in and compute the keys and values for. So they do not mention, I think this here is only for the second attention mechanism, but I'm not too sure. They don't really mention it, because the index set here is related, this index set here is described in the second part, so just for the selection, the second selection attention mechanism. So I'm not sure if they use this kernel to compute everything, which would be a bit strange, because they mention that they are loading in things sparsely, and for the first attention mechanism, that's not sparse, it's just a compressed dense representation, and for the third attention mechanism, which is the window one, it is sparse, but it's just along the diagonal that you're loading in. So this seems just to be the kernel for the second attention mechanism, the blockwise selective attention mechanism. So, whenever they mention kernel, I'm guessing it's just this part, but they could have also implemented a kernel for the rest. They don't describe that in the paper. They also don't have code, so I can't look to see, they actually do implement a Triton kernel for all three attention mechanisms, but the explanation they have here just seems to work for the second attention, that they have. And intuitively, you can utilize, there already exist kernels out there that are efficient for window attention, and for the first attention mechanism, you can use something like flash attention, because assuming you can make it causal. The first attention mechanism is just it's not dense; it's just compressed. So yeah, that's that. Maybe they use Triton to speed up the addition, like the accumulation of the attention outputs, but I don't know. That's not something that they mention explicitly. But let's go to the experiments. So what they show is that they have slightly better performance than a normal full attention. So if we look at their attention mechanism here, it has slightly better results in terms of the loss on this pre-training task that they do using some 27 billion parameter model. So pretty good size. on some data that they're training on. But if they're training in the exact same way for full attention and this NSA attention, and they show it does slightly better. Maybe that's because there's an MLP that gives you more parameters and that makes it slightly better, or maybe it's because it is better in general. It does make sense for it to be maybe a little bit better. I can kind of see that because you're adding 3 different attention mechanisms together, where one is kind of global representation, that is this global smooth representation of your sequence, while the others are sparse representations. So you're still getting information from, or you're getting local information and global information still, just in different ways. So I could see maybe it does a little bit better, but yeah, it's not too much better in the end. Like, it does better in general, but I wonder if that's because of some other reason. I don't know. One thing that would be interesting is if they actually ablated this and said, oh, if we only had window attention, maybe it gives you a curve like this and it's not good. But if we and if we only do our attention mechanism where it's only the compressed representation, it also doesn't do too good. So I would love to see some ablations for this. Do you actually need the fine grain representation? I don't know. But they don't have that in the paper. They don't have any ablations. All we have is the final 3-way attention that they have. Yeah, so here are the parameters that they use. They use a compression size of 32. So the window size is 32. The stride is 16. The output window is 64. There are n is equal to 16 selected blocks. So whenever you're looking at in the second attention mechanism, you have 16 blocks that you're choosing. So that'll be a total of 16 by 16. That'll be how many keys you keep in the second attention mechanism. And W is equal to 512 sliding window size. So yeah, I mean, you get a lot of sparsity with this. Some more results that they have. It does pretty good. Performance comparison. They show it does well in needle in a haystack. Always good to see. If it doesn't do good in needle in a haystack, it should be you're using softmax attention. And here, this is kind of the big graph. If we look at this, they say it has massive speed up. Like, the speed up is crazy. So blue is flash attention 2, orange is sparse attention kernels, and green is compression and window attention. So this here is, I think, the kernel they develop. Green is the first attention mechanism and the third attention mechanism. So window attention already exists. You can just get a kernel offline for that. Compressed, that's just full attention, but in this compressed representation. And they show if you add the kernel that they propose, which I think is just the kernel alone, and you have these other 2 attention mechanisms you use, then it has this insane speed up. So that is cool to see. And that's because you get so much sparsity. Like with, I showed before the complexity, and the complexity was kind of bounded by the compression representation. And with the compressed representation, it's way smaller than the n squared. So that's why you get the speed up here. Also, the kernel they develop is really efficient in terms of sparsity because they use this blockwise manner. You can load blocks quickly. You can't load a sparse matrix quickly. You can't do computations with that quickly. And then they show this expected speed up, which does not matter because this is theoretical. So the actual speed up is what you have here, which is awesome to see. And yeah, I don't think they have any more results. They kind of have these here showing, yeah, it does do a little bit better than full attention for some reason. And I'm very curious to see why it does so much better. That's very interesting to me. That it's not just faster, it's better. But yeah, that is this paper here, native sparse attention. Not too complicated. They do a lot of different attention mechanisms, global, and sparse and global representations, local representations, both are sparse, and it gives you a lot of speed up. I'm very, very curious to see if this is as good as they say it is, if it gives you as much speed up as it does. We're already seeing Lucid Arraigns do an implementation, so we're seeing people implement this already, and I'm very, very curious to see how good this actually is.